Hi everyone, and welcome to today's session. So for today, we'll be covering R0. It's basically a training paradigm for LLM to learn from itself. So as you see from the title, they want to evolve the reasoning of the LLM from zero data. So just a disclaimer here, it's actually not zero data. The LLM still needs to know some basic knowledge so that it can generate questions for itself, and then it can solve those questions. So how they do this is an iterative training process where there's this person called a challenger who will generate the questions. And the aim of this challenger is to generate questions that are hard, but not so hard. You want it to be hard enough to challenge the solver to solve those questions, but you don't want it to be too hard that the solver is completely clueless. So it's something like, a training regimen. You train someone to the edge of their expertise. You keep giving them harder and harder tasks to do that are manageable, but not too difficult. So that's the role of the challenger. And then there's another thing called the solver. And this person, the solver, is basically taking the questions from the challenger and solving them. And both of them, they will be reinforced. The challenger will be reinforced to give better and better questions that challenge the solver. The solver will be reinforced to solve the questions better. And it's a very nice process that ultimately, hopefully, makes the LLM improve, because the LLM will be both the solver and the challenger, right? So this sounds complicated. So I've prepared a very nice example that's not in the paper. So I came up with this example. So enjoy, all right? So imagine you are in school, all right? And your teacher is like, I'm not sure about the capabilities of my students. So let's see how good they are in class. So the teacher asks, hey class, what is 1 plus 1? And then the students answer, 2, 2, 2, 2. Everyone answers 2. It's like, then the teacher is like, oh, I think that's too easy. If I ask this on the exam, everyone will get full marks. So I better not ask this kind of questions for the exam. So then the teacher thinks to itself like, let's try something harder. And so the teacher asks, class, what is 1 plus 2 plus 3 plus 4 plus 5 until plus 100? And then the class took a long while. Okay, they took about 1 minute, 2 minutes. And then suddenly the first person just says 1,000, and then next one 110, and the last one just gives up, says 0. Right? And then the teacher knows, I think this question is too difficult. If I ask this, no one will get anything correct, and that's not a good question to set for my exam. So then the teacher thinks to itself, to himself, like, maybe we make it a little less difficult, something easy, but not as difficult as this. So I asked, the teacher asked the question, so class, what is 1 plus 2 plus 3? And then you can see two people in the middle raise their hands and say 6 is 6. And then the one at the left, after a while, like, okay, I think it's 4. And then maybe the one on the right says, I think it's 5. And the teacher knows, looks like there's some consensus vote here. Looks like people are converging to some answer. I think this question is all right. Just bear in mind, this teacher is a bit of a lazy teacher. The teacher doesn't really know the answer. All right, the teacher just comes up with the question, but the teacher doesn't know the answer. It's like, if you are being plugged in to be a teacher for a topic that you're not familiar with, maybe you read the textbooks, you can come up with the question, but the teacher doesn't know how to solve them. So the teacher is relying on his class. You see, if based on the class over here, everyone is getting it consensus. This must be correct. My class must understand. So if everyone gets it differently, it's like, I think this question, maybe no one really understands it, so better not ask. And then this question is like, oh yeah, about half of them answered correctly. So it means that it's probably correct. So this is the catch for this teacher, right? The teacher doesn't know the answer. There's no objective ground truth here. So just based on this, the teacher's like, okay, I think this the majority answer, this should be correct. All right, so then the teacher says, all right, let's take all these learnings and I'm going to set my exam based on that. So, based on my learnings here, this kind of question, 1 plus 1 is too simple. Let's not set there. This kind of question, 1 plus 2 until 100 is too hard. Let's not set this kind. So, deep inside the brain of the teacher, the neural networks, like they fire and then they get reinforced to say, okay, we should set this kind of question, 1 plus 2 plus 3. Do more of this kind of question, do more of this. And so in the exam, the teacher has increased one level. Okay, before that, teacher was level 1. Right? The teacher doesn't really know what to set. But now after gauging feedback from the class, the teacher now knows, yeah, I should set questions that are addition, but maybe adding only like 2 or 3 digits. All right. So the class gets the exam. The exam, one of the questions is, class, what is 4 plus 4? And as usual, the lazy teacher doesn't know the answer. The teacher just knows how to set the question, because this teacher, it can be a plug and play relief teacher, what doesn't know the topic well enough to know the answer. He just knows how to set the questions. So as usual, the 2 students that are in the middle of the class, they write down their paper 8. And then the one on the left took a while, and they're like, okay, I think it's 5. And the one on the right is, I think it's about 6. So then the students who got back the paper, because they are marked correct, these 2 students are marked correct. All right, we can give them a name. All right, we can give this student, we can call this student Peter, and we can call this student Alice. All right, and then maybe this is Bob and this is Dylan. Okay, it doesn't really matter. So maybe the 2 students, Peter and Alice, they got their paper back and they got full marks. Wow, I'm doing it well. I'm learning well. And they get rewarded to do the same thing again and again. All right. And then these 2 people here, Bob and Dylan, okay, if you don't get the question correct, what will you feel as a student? You feel, I don't know, feel a bit unhappy maybe, or then they start to talk to Peter and Alice like, hey, how do y'all do it? And then they kind of learn, all right? So in practice, all 4 students, they share the same mind. All right, it's a little different from us right now. We have different individual consciousness, I guess, like individual thinking processes. Here, all 4 students are part of the same brain. All right, they just split into 4 different instances, and they can learn from each other. So this student Dylan gets negatively reinforced. He feels like, I think my studying method is wrong. Let's try something else. So they learn from the people that get positively reinforced. And all in all, after this alignment process, all of them can answer it. All right. So let's see the next slide. So the students, they are not static. They learn. All right. They learn from one another. And when the teacher asks the question again, class, what is 4 plus 4? And then the next day in the class, everyone answers correctly. Everyone's like, 8, 8, 8, 8. Then the teacher is like, oh no, the question is too easy. I need to ask harder questions. All right. So both of them have leveled up. And so then the teacher would probably go through the cycle again and say like, hey class, what is 4 plus 8 plus 12 plus 16 and so on. And the class probably doesn't know anything. Then the teacher maybe says like, okay, what's 4 plus 8? Then maybe 2 of them get the right answer, 12, and then the other 2 didn't. So the teacher knows, okay, I should set harder questions, but maybe adding 2 digits only, but make the digits a bit larger. So the questions evolve to become harder because the teacher knows that the class has changed. After setting the first exam, the class has learned. And so it's not good to set the same questions again because there's no kick for the students, all right? You can't differentiate people on a bell curve if everyone gets the same score, all right? I mean, I don't really agree with the bell curve concept of learning, but in terms of knowing how to teach, you need to know like, okay, how many people know this subject, how many people don't, and then you set a balance, don't make everyone unable to do it. All right. So the teacher is learning from the class, and then the class learns from the teacher as well. When the exam is over, they discuss and then they learn. So can you all see that this process of teacher and student is exactly what I talked about just now? Challenger and solver. The challenger comes up with the questions, the solver solves it. And actually, none of them know the correct answer. So it's kind of like the blind leading the blind. I'm not sure if you've been to places whereby people discuss stuff, but they don't know the correct answer. Like maybe, they talk about the future of AGI, maybe. Everyone's talking about AGI, but actually no one really knows when we'll get there. And then all is just talking about numbers. So 2030, 2028, like Ray Kurzweil say the singularity is nearer, that kind of stuff. But no one really knows when. So, that kind of thing, eventually people will just, revert to either the most influential or the consensus answer. So over here, we go with the consensus answer, the one with the most number of replies that are the same, will be sort of the view that everyone holds. All right. So I'll just pause here for a while. Any questions, comments about this? because this is exactly what we are talking about today. In fact, we have covered everything that I need to cover for R0 in these few slides. But I'll go through the math later. But before we go through that, just want to open up to the floor to let's discuss, like, what do you think about this process of learning? Is it good? Is it prone to error? Like, what do you think about it?
Well, without a ground truth or any verifier, there's a possibility for loops between the challenger and solver, aren't there? Or is there a mechanism that allows for those loops to be accounted for when going through this training process?
There isn't. So it is possible that you can be reinforced to get the wrong answer. And then based on that wrong answer, your next cycle will generate more questions that are based on that wrong answer. Yeah. And when the solver solves it 50% of the time, like the students, these two answers might be wrong, like this can be wrong. And then we can negatively reinforce both the teacher to ask questions that the teacher thinks is challenging, but actually the students got it wrong. And the students get reinforced to think that, hey, these two questions are actually correct when the answers are wrong. So, it could be a negatively reinforcing thing for both sides. Yeah, so that is a possibility. Yeah.
Sounds good. I think those are all the thoughts I have right now.
All right. Anyone else? Or good to go? Okay, let's move on. So this is essentially the whole process of this paper. We start with a base model. The base model asks the questions, and based on the solver's response, so the challenger has access to the solver, all right? So they can gauge, okay, how many of the instances of this solver got the question correct? I mean, not correct, but how many of the answers are similar? Because as you know, the challenger doesn't know the answer, right? And then you see how many of them are similar. It's about 50%. That's a good number. So I ask questions that are about 50% solvable. The solver tries to solve them and gets rewarded for being close to the model answer. And the model answer in this case is just the majority answer of the solvers. So the class marks itself, actually. Like, the most common answer in the class is the correct answer. All right. And then we have the new challenger that uses this solver to come up with the questions, and then comes up with a new solver to answer those questions, and so on until we decide to stop. Okay, so sounds great in practice. And the thing about having no data and learning from no data is actually a misnomer. You kind of need data, because if you don't have data, how can you ask the questions, right? How do you know what questions to ask? Especially in very specialized topics like math, chemistry, law, maybe. You kind of need some ground knowledge to even ask those questions. Sometimes the questions you ask reflect the state of understanding of yourself. So if you know nothing about that subject, it's very hard to ask good questions. So you kind of need the base model to already know the topic. Then they can be trained to ask better questions and also to learn better answers. So let's see how this works, okay? So they tested on a benchmark, I believe, are all MCQ questions, GPQA, super GPQA. Now we have evolved to super GPQA because GPQA is too easy. And also GPQA has a lot of wrong answers. So we have math, we have the MMLU. So all this, if I'm not wrong, they are like multiple choice understanding questions of various domains. I think GPQA is about science, math is about math, MMLU is about language understanding. Okay, so you can see that the base model, which is the Quen 3.4b base, okay, it's not an open source model, it's not a closed source model, it's an open source model, so they can train it easily. You can see that after they train it, it gained 31.9% is percentage points with relative to the base, but they gain about 7% percentage points improvement, about 7 here for math as well, and this one is the biggest, about 14% improvement. So you can see that there is some benefit to using R0 to do the question and answering, because you learn from more questions and answers than your training data set. Okay, so essentially your challenger is generating synthetic data, and your solver is generating synthetic answers. So you can see that it's kind of like you learn from yourself. So essentially, nowadays, especially like in Singapore, the learning is like, you teach less, learn more. I mean, that was during my era. They want the students to learn on their own. Yeah, this is probably what you can get when your students learn on your own. But you might learn wrongly. So there needs to be some supervision, which is kind of lacking in this R0 paper. Okay, but the idea of generating the questions, generating the answers, and trying to improve yourself based on those questions and answers, this is a good idea. All right, let's move on. So what is this term here, GRPO, Group Relative Policy Optimization? Okay, I forgot to put the full name here. So let me do it. So this word actually appeared first in the DeepSeek V3 and R1 paper, where they kind of invented this term. All right, because previously the one that was known is called proximal policy optimization. Okay, there's an I here. Okay, so this is basically a way to improve based on the experiences in the world. Like based on what you experience in the world, you reinforce the positive actions and you de-reinforce the negative outcomes for those actions. Okay, but this requires some form of ground truth. The environment needs to give you your reward, all right, in proximal policy optimization, because you need to know what is good and what's bad. Okay, so the environment gives you a reward. GRPO is a bit special. GRPO, it is your peers that give you the reward. Okay, of course, the peers that give the reward, of course, the reward that each person gets is still based on some environment. Okay, because everyone still needs to be assigned whether it's correct or not. It's just that now with the peers, you sort of average out your dependency on the environment. Like you can still see, okay, who does better, who does poorer. Okay, so group relative policy optimization focuses less on the environment and more on the groups around you. Okay, because you can just give any heuristic. You don't even need to base on the real environment reward. You can just say, people who pass stage 1 of the test gets 1 point, stage 2 of the test gets 2 points. And you can even use a heuristic that is, not even true. Like the reward need not be ground truth, right? Which is what they did in this paper, right? So this, of course, ideally, if your environment gives you the reward that is the ground truth, that's better because you can, learn better. It's always good to learn from the actual signal than a bootstrap signal. So what's the idea of GRPO? Look at these robots here, right? Some robots do well in the environment, all right? And the environment is, as I said, you don't need the real environment reward. You can just use a heuristic, right? You can just give an arbitrary thing like if you walk 5 steps in front, you get 1 point, that kind of thing. And you will be reinforcing that kind of behavior, all right? To move forward 5 steps. Yeah. So this kind of tick means that they have done better relative to the group. Okay, so this is very important. Relative to the group. So that means there are some people who didn't do very well. So some people don't do well, they'll be penalized. Okay, they will be told, hey, you can learn from those who did better. Okay, you are doing the wrong thing. So peer learning is very, very influential. And I would say that most of evolution is based on peer learning, right? We learn from one another. Good traits get shared quite easily. Good learnings get passed down quite easily among the species. And if it's not passed down, at least those people who learn the good traits will survive better. So for humans, the knowledge is passed down because we share knowledge with one another, right? Internet, social groups, and so on. Peer influence is huge. I can tell humans are such a big social group. And that's probably why we evolve so quickly. Because in social groups, knowledge is shared, but knowledge is shared in a very uneven way. All right. Only those who kind of are perceived to do better gets more influence and those gets passed down. That's why we have stuff like quotes from very famous people. We kind of have identified them as successful people, like maybe Steve Jobs or Nelson Mandela, who did great things for the world. We learn from them, but we don't really learn from nobody on the street, right? So that is kind of how we evolve as humans. GRPO is very, very similar. We learn from those who have achieved great performance in the world. And as I said, the performance need not come from the world itself. We can just give an arbitrary heuristic that we want, and we can learn from them. So based on that, everyone like is a hive mind. Everyone gets downloaded. The information gets downloaded and shared, and everyone improves. So some responses are good, we learn from them. Some responses are bad, we don't learn from them. Okay, try not to repeat them. And we learn from the ground and objective reward, okay, which is like in math, you have a model answer if you have the model answer. If it's a programming question, you have code. Okay, you can run the code and see whether it works for your test cases. This paper, okay, so the original GRPO when used in DeepSeek. So this was the DeepSeek R1 kind of method. Uses an objective ground truth, which then you can for sure know that, this reasoning traces to get this answer is correct. This paper doesn't have a ground truth in R0. So we just take the majority response, and the big question we have is the majority response good enough? Okay, because we are already learning from one another, right? And if you are learning from one another with these signals that are correct and wrong being determined by the group as well, that's like a double bootstrap. Like we learn relative to each other, and we also learn from the consensus of each other. So if the consensus is wrong, then everyone is wrong. I mean, if you think about it, this is something like blockchain, right? Like blockchain, you have the 51% attack. I'm not sure if you are familiar with it. Like the data is stored on computers distributed. And then if, let's say, majority of the computers agree that the transaction has occurred, that transaction has occurred. So it's like building some form of resilience based on communal knowledge. But this is different because this is not really bootstrap. This is, you already learn this from some actual occurrence. Okay, where in this kind of majority response for the R0, the data is actually all generated by yourself. It's not okay. Actually, blockchain also has this. Okay, let's not confuse this with blockchain. I thought blockchain was more secure, but no, you can also fake it. So you see, this is the problem with communal knowledge. How do you know what is correct? How do you know what is not? And if you use a group consensus to do it, you will never know whether your answer is correct. Okay? Because group consensus is very subjected to those kind of group thing, right? Everyone thinks the same way, then we will learn new stuff, right? So this is one of the fallbacks of this paper. So let's take a look at the math. All right, this sounds a bit scary here, but let me just do a very, very simple description of this. So we have a large language model that has a policy to generate out tokens. All right, so based on this policy, given like the input sequence generate the token, in this case is a response, probably an MCQ response. So what we want to do is we want to learn a policy that can generate out a response, policy that will generate out a response X. Okay, X given the sequence of inputs. Okay, so the inputs maybe is like Y, 1, 2, N. Okay, depends on how long your Y0. Okay, Y0 to N. Right, we always type 0 in computer science, and then we also have the policy has this theta. Okay, so you have a theta here. So essentially, your policy is telling you how to generate the next token based on earlier tokens and condition on the learned weights and bias. So essentially, this is your policy for an LLM, large language model. You want to learn how to generate out the response. And you are training this using a reinforcement learning method. Of course, you can also learn this response thing by training them on sequence. So it's like if you have a question, it's like, what is 1 plus 1? And answer is 2. Question, what is 2 plus 3? And then the answer is 5. You can also learn by next token prediction. You can learn this. You can treat this as this could be your input. And then you can learn the next token prediction of your output like that. But people have found that if you use GRPO, you actually learn more effectively than doing this supervised learning. Okay, so this probably only like affects like the output for this one token, while this kind of GRPO training can affect the tokens anywhere. Okay, so this is a little more efficient, but the idea is very similar. Okay, you want to reinforce the model. So you want to reinforce the model to output correct answers more often. Okay, and then you want to penalize models for outputting the wrong answer. Okay, so I guess in supervised learning, it's a bit, I mean, in next token prediction for self-supervised learning, I think it's a bit harder to, do something like this. Like wrong answer for, like, how do you want to express this to the model? Like, you kind of need to have like a new term wrong answer, and then this answer could be many, many different answers. And it's very hard to learn next token prediction like this. Whereas if you learn using GRPO, you can actually have the model learn the wrong answer because it's penalized directly in the model generation process. Okay, so I would say, I mean, last time I was thinking, why can't we do supervised fine-tuning, right? Or let's fine-tune correct and wrong answers like that. It turns out it's actually harder to do that because it's very hard to express correct and wrong answers as a next token prediction objective. If we do it in GRPO method, you affect the model generation directly. So it's more effective, I guess. Yep. So this is the kind of math for the advantage. Each response will get a reward based on your environment. And this environment is basically saying right or wrong. Okay, this is a 1 or 0. And the environment in R0 is that if your answer is majority vote, 1. If your answer is not, 0. Okay, very simple environment score, right? So you can see that these are your scores that you get, and you minus off the average of the group. So it means that if your group is doing like this, if your group is getting 1, 2, 3, 4, 1, 2, 3, 4, the average is 2.5. So essentially, the first person will be negatively reinforced, and then the other two will be positively reinforced because 3 is greater than 2.5 and 2 is smaller than 2.5. So your advantage term, all right, is positive if you are above the group mean. Means if you perform significantly better or even marginally better than the group average, people will learn from you. And if you perform worse than the group average, people will learn from you as well to not follow in your footsteps. All right. So GRPO is a very powerful group learning system. Right, and then we also divide by the standard deviation to have training stability to make this term not too big, right? Yeah. So these are just some tricks. Can you see that this term here, and does this look familiar to you? Right. So if you are familiar with normal distribution, this is exactly like how the normal distribution is. Like you take your term minus your mean, minus divided by the standard deviation. All right. Can't remember the term for this standard deviation. Maybe x hat or something. I can't remember this. This is a statistics class, X tutor or something. You have to check the textbook for this, but this is essentially a normal distribution. You minus the mean and you divide by the standard deviation, right? So we are learning from the average of how well people do, and we update this in the policy. Okay, so this policy is basically actually for PPO, we only have this term here. All right. We actually just need this term here. They just added this term here to like play safe. All right. So just explain briefly what this does. You have your new policy, you have your old policy, and what we want to do is we want to make sure that this doesn't go too far away, all right, from this policy. So there's actually a step limit to regulate it. And so actually this is the advantage term for the policies. Like this is used in RL quite often. And this is to make sure that we don't step too far away, all right, from the original policy. So we have some clipping mechanism, and yeah, essentially we want to learn from this advantage, but we don't want to learn. Let me write this down somewhere. Learn from the advantage term, but not too much to affect the current outputs. Right? We want to learn, but we don't want to learn so drastically that we change completely who we are. Essentially, that's what this term is saying. Okay, this term at the back is not really required. This term at the back is basically saying don't change yourself too much. Okay, why? Because KL divergence is 0. if both distributions are the same. And KL divergence is 1 if both distributions are different. So like if you have two distributions and both of them are the same, like for example, this is your distribution, this is your PX. Oh, sorry, this PX. PX is the probability of X occurring, and then your X is here. If one distribution is like that, and the other distribution is like that, then the KL divergence is 0, right? But if let's say the other distribution is something like this, then the KL divergence is, KL divergence is greater than 0, which then you are penalized because you want the distribution to shift in the output tokens, but you don't want it to shift too much. You just want it to shift enough such that you learn from the group average, but you don't change your distribution too much. All right, so this essentially summarizes GRPO. I spent a bit of time here because the paper uses GRPO a lot. All right, any questions so far for GRPO? All clear about how GRPO works? Okay, so essentially learn from the group average, but don't learn too much. Okay, because we don't want you to affect your previous learnings too much. All right, so this is how the challenger and solver works. You have this challenger here that you freeze the solver basically. So it's like giving the teacher some snapshot access to the class. The teacher asks a few questions, learns how the class responds, and based on this majority voting, all of them will give a response. Like student 1 will give response 1, student 2 response 2 and 3 and 4 and so on. Each of the questions the teacher asks, you will get a majority vote. So you learn through different questions. So these are different questions. And then these are different answers. So the challenger will come out with the question, the solver will take these questions and get the answer. And the teacher will learn. The challenger will learn to output questions that lead to 50% solve rate. And the solve rate here is actually in quotation marks because it's not a true solve rate. Okay, the solve rate here is based on majority vote agreement. All right. So the challenger is essentially motivated to get questions that are hard but not too hard. And then after that, the solver would take this teacher that has learned how to set the questions, frozen already. The solver will learn from each other to basically learn how to get the majority vote. All right, so essentially, we keep repeating this and we have the whole loop. Okay, so I won't be covering too much for this because, the illustrated story that we told at the beginning sort of covers this already. And you can see GRPO is used everywhere. It's everywhere. GRPO is used for the teacher of a challenger. GRPO is used for the solver. And for the reasons I mentioned earlier, GRPO is a little more effective. In fact, a lot more effective than using supervised fine-tuning. All right, so these are the steps. Step 1, challenger trained to generate better questions that are challenging for the solver. Okay, and these are synthetic questions. Step 2, you get your new data set using this synthetic questions. Okay, we don't just take the challenger and directly ask the questions. Okay, we still need to do a filtering step to ensure quality questions. And this filtering step is make sure questions are of the right format, because sometimes not so good LLM might generate wrong format questions, all right? Especially if you don't use structured output formats like what they did in the paper. They just prompted the LLM to generate the questions in the question text and the answer in the answer tag. Yeah. So filter, make sure the questions are of the right format. And you also want to make sure approximately 50% solve rate for each question for the solver. Okay, so we already do a pre-screening for these questions to make sure that they are difficult, right? After that, solver gets access to this data set, generates their answer, and then they learn to get the majority vote answer. Right, so there are 2 steps here, and then you repeat the steps again and again and again and again and again and again and again. But you can't repeat too much because we will see later there's some problems with this method. All right, so step 1, train the challenger, make the challenger make the solver solve the questions 50% of the time by asking them the right questions. All right, so we need to train the challenger to ask the questions. So we define this term called the uncertainty reward that guides the challenger to produce challenging yet solvable questions. So they define an uncertainty score, which is basically how many questions are there that is similar to the pseudo label. And the pseudo label here is generated by majority vote. All right. So we see how many of the responses are correct. If you run the solver multiple times, maybe with different seeds, see how many questions are answered correctly. If the question is answered correctly 50% of the time, which in this case is a half term, you can see that this equation here would become half, and half minus half becomes 0, and then 2 times 0 is 0, and then the reward is 1. All right, if we have the uncertainty here being 1, then this 1 minus half is half, and this 2 times half is 1. And if this is 0, the same thing happens because this is an absolute value. All right, so essentially reward 0 if everyone answers correctly or incorrectly. Okay, and reward of 1 if if 50% answers correctly. So yeah, this is something that is what I've been saying again and again. This is in the math format. So you can see math is hard to understand. It's easier to do it in analogy. That's why I like analogy more. This kind of reminds me of a game I've been playing. This called Dixit. I'm not sure if you heard of it. Dixit is where you have a storyteller tells a story. I mean, it can be like a word, and then everyone puts a picture, and then you want people to guess your picture correctly, but not all guess correctly. So yeah, I mean, it's in some sense, it's like how do I put it? You want some people to fail, and you want some people to succeed. Then you can have some score differential. So something like this, but Dixie is not 50%, right? They say as long as 1% guess your picture correctly and the rest guess it wrongly, you are good to go. All right. So have you all played the game before? Dixit, by the way. I'm not sure whether it's only for me, but yeah, there are games that are based on this uncertainty score, and they are quite fun to play. All right. So this is essentially what we reward the challenger to do, to solve to get questions that only the solver can solve 50% of the time. And we have this very complicated term here called repetition penalty, which in simple terms says that we should make the questions diverse so that people get access to different kinds of questions and not only the same ones. All right. So this is something that I think GANs didn't do very well, because GANs is the generative adversarial networks. Okay, GANs. Okay, they didn't really do this thing very well because you can have mode collapse. So GANs is you have a generator generating a picture, and then the discriminator discriminates the picture, identifies which class the picture is. So you can see that the rewards are very sparse here, because you only get reward if the discriminator gets it right or wrong. That's like very, very rare. You can either have everything getting 1 or everything 0. So if you fool the discriminator all the time, the generator might just generate the same picture all the time. Yeah, so this is a key thing. Question diversity is a key challenge for teacher-student networks. Okay, because the teacher will be very incentivized to just come up with the same question for your test all the time. Like in AlphaZero as well, you kind of don't want the teacher to just keep playing the same moves again and again. You want diversity so the student can learn for stuff. So like even in AlphaZero, where you have self-play, I believe the first 30 moves are random during training, so that you have diversity of bots. Yeah. So this is a very important thing. Okay, so I can't remember how many moves, but I have to check the paper again. But you still have diversity in this. So having diversity in your questions is very important, okay? Because you don't want to just learn from one thing. That was too narrow, all right? In GANs, we call it mode collapse, okay? Mode collapse is generator only generates one kind of thing, right? We don't want this to happen. We want things to be broad and diverse. Okay, we want lots of things to be generated. And so in this paper, they use this thing called the blue score. And the blue score is basically something that says that how similar are my two chunks of text. This is used in natural language processing where they use n-grams. N-grams are like how many words are similar together. Like I am, that's a 2 gram. Then you have 3 grams. I am and that kind of thing. So blue score is an algorithm to generate similarity scores between two chunks of text. And if the two chunks of text are similar to each other, the score is 1. And if the texts are not similar to each other, then it's 0, right? So essentially, based on the blue score, we come up with different clusters for each of our questions, okay? And each of these questions will then be fed into a cluster, and we kind of don't want the cluster to be too big because each cluster means different kinds of questions. Like, so in each cluster, okay, the penalty is based on its relative size. So the more question there are in that sector, so you have like cluster 1, cluster 2, and cluster 3. The more questions are in a sector or in a cluster that, like, if let's say you join a cluster that is huge, if this cluster is like 10, there's already 10 people here, and there's 1 here and 1 here, you have a very negative penalty for joining huge groups, huge clusters. Okay, we kind of want to only join clusters that are small. Okay, so you have small penalty here. To me, I think this is a horrible way of getting this diverse questions. Okay, because this is a reward score, right? This is a reward score that interferes with the uncertainty reward that we saw earlier. This reward score basically is like saying, hey, I kind of want to penalize my questions for being in the same kind of question. But you use stuff like blue, it's very hard to back propagate all this. So essentially, the score that is given to the LM is just it's some black box. You don't even know what's going through there, and you get -1. Why did I get -1? Then you go through the black box, like, I got minus 0.5. Why did I get minus 0.5? I don't know. This black box just tells me I'm minus 0.5, but I don't know why. Essentially, that's what the LM is thinking, because you don't backpropagate through blue. Okay, you can't backpropagate through an algorithm, right? So this is a very bad penalty in my opinion. Like, I don't even know whether this affects their results. Okay, if you remove the repetition penalty and replace it with something else, maybe they'll get better results, because this definitely affects the loss term, right? So you can see that we we have to avoid repeating questions, but they do it in such a way that the LM doesn't really know why it's being penalized. It just knows that this question is bad, but it doesn't know why it's bad. And the same kind of question can be good. If your cluster is little, that question can be good, but if the cluster is huge, then the question is bad. The same question in a different setting can be good or bad. How is the LM going to learn from this? Okay, so I don't really like this penalty score here, right? So next penalty that they have is a format penalty. Is basically saying that if there's no question text correctly and there's no output text in the right structure, you will just assign a reward of 0. Essentially, this is like a reward mechanism to let you learn how to generate proper questions. Okay, this is not really needed if your model generates the structure output really well, right? So putting all together, you can see that we have a composite reward, okay, that is based on the uncertainty score. Remember, this score is a 1 if solver gets it right only 50% of the time. And this repetition score is this penalty is 0 if the cluster is small. In fact, I don't think it will ever be 0, because if you look at the repetition term earlier on, you can see that it's always lambda ck over b, right? And your ck is rarely going to be 0. There will always be some term here, so you will always be penalized. I'm not even sure whether they scale this down to the they scaled to the batch. So yeah, your clusters will never be this whole term here will always be smaller than 1. All right, so it is I'm not sure whether it's going to be smaller than 0.5. So it's very possible for your reward to be negative. Okay, because your cluster here can outweigh the uncertainty score. All right. I suspect there's a problem with this repetition score, although I cannot confirm it. Okay, because if this is done in the same loss term as the uncertainty and this overshadows the uncertainty, I'm not sure whether the LM is learning from the black box, which it can't learn from, or is learning from the true uncertainty score. So in my opinion, it would be better if we take away this repetition score altogether and just focus on the uncertainty. And then maybe we can do a post-process filtering to generate your repetitions. Or you could just prevent repetitions via prompting. When you generate questions, you ask the LM to generate only for one category. And I think that's enough. Don't use the repetition score. Don't interfere with your loss term for uncertainty, which is already going to be very difficult to get a good question, because how do you know whether the solver gets it right 50% of the time? There's a bit of guessing here, it's like there's some guesswork involved. And if you're already having a guesswork game here, you have another guessing game at the other side that interferes with your first guessing game. It's like, you're playing casino, you have two games. One is one is a roulette, and you have a second roulette, and then you have no idea where your score comes from. Your score is a combination of both views. I have no idea how the LM is going to learn from this. Okay, but it still learns, all right? There's still some merit to this method, but I think the repetition score should be removed. Yeah, my own personal opinion, all right? Okay, so this is the GRPO loss here that we learn from this reward, and then we compute the advantage as we seen earlier. Okay, so this is how the challenger updates itself to solve better, to get better questions generated. Okay, I think that's all for the challenger. Any questions so far? I've covered through a lot of math, a huge chunk of math, because the paper has a lot of math. I hope you can follow. It's all good. Maybe give me a thumbs up if all's good, so I know all's good. Okay, that's great. So let's move on to the next part. This is called the solver. So now that we have our data bank of questions, let's try to solve them. So first we create the data set. We first pull n candidate questions from the policy of the challenger, and each question we obtain m answers from the solver. And then we have a pseudo label via the majority vote of the solver. All right. Basically, we get our answers from the students before the exam even starts. Okay. And make sure that the answers in majority vote, or make sure that the majority vote is close to 50%. So we do a final check. Okay, because early on when we do the loss function, maybe not all the losses in the uncertainty loss. Like maybe you don't really, or maybe in the training wise, your uncertainty loss could be a certain percent, 30, 40%, or 50%. But after you train enough for the whole batch of learning, your uncertainty might shift to maybe 70% or 30%. So like because as you learn all the questions in the earlier step for the challenger, your initial probability might shift. So we do a final check. Once we generate these questions, we do a final check that these questions are indeed only solvable about 50% of the time. Okay, and we have this epsilon term that basically, this is not epsilon, this is, I can't remember the name for this math signal. Sigma, is it? No, not sigma. Epsilon. I can't remember the name for this symbol. Yeah, but basically with a very, very small term, maybe it's epsilon, yeah. For a very, very small number, we want to make sure that the probability of the solver getting the question right is very, very approximately 50%. All right. So this is basically a filtering step that they do. I think this is a genius step, because the way that the LM learns is by good data sets. So filtering, if you ever do a LM pipeline, filtering is a very important step. You don't want to learn from all data. We want to learn from quality data. And that's what we learn from like papers like 5.3, where you learn from quality code, tiny stories, where you learn from quality stories, I guess. Yeah. So your data set is very important. So this step is a great step. Next, we have a solver, and the solver basically is saying that, if your answer is the majority vote, you get 1 point, one score, if not zero. Then we learn using GRPO to make sure everyone learns the majority vote. Okay, I won't go through too much for this because I think this is quite straightforward. All right, let's take a look at the results. All right, so we have a few benchmarks. All right, they have the math benchmarks, Super GPQA, MMLU Pro. You can see all these are upgraded versions of their original counterparts. All right, we have moved so fast in the deep learning field. All right, and we have Big Bench, extra hard. All right, so you can see that maybe the next one is astronomically hard, that kind of thing. Yeah, we have moved quite a lot here because LLMs actually, if you give them the question and answer, they can solve everything correct. Right? If you train them enough on the test set, you will solve everything right. So there might be some test set leakage in all these benchmarks, but the LLM is definitely learning from it. So you can see that the results for this, we have the base model for here, and the base model already has some understanding of this. You can see that they already have a non-zero accuracy score for all these benchmarks. And as you iterate, okay, the challenger can also, you can see how good the teacher knows the answers. The teacher actually, the base challenger itself, after you train, just by training on the solver to make the solve rate 50%, it's interesting, right? Just by training on the solver, you already improve the accuracy for your challenger. When you ask the challenger to solve the questions, he actually learns something. So this is something quite interesting. So what it means is that if you teach someone, you can actually learn a significant amount. And in fact, this challenger did not even teach them. They just learn how to ask the right questions. I rephrase it, okay? If you learn how to ask the right questions, you can actually learn a significant amount. Okay, just just the learning how to pull the solver 50% of the time already led to significant performance improvements in your challenger. Can you see that? Can you see that? We could just jolly well end at this step. Okay, but not all have a positive increase. Like Big Bench extra hard is negative. All right. So this is not a reliable training step, but somehow it works. It already improves performance. In fact, if they stop the paper as here, learning how to ask the right questions improves answer accuracy. I think that's a nice paper as well. All right. But after they do the R0 method, where you learn the solver to solve this using GRPO, wow, huge jump. Actually, the solver learning from majority vote is the key here. You can see the jump is huge. So I have another statement here. Solver learning from majority consensus can be significant. All right. So it can be significantly good or bad, but here is, I would say, good. So you can see that there's some learning here. Then you might ask yourself this question, like, is this learning continued or is just one-off? And then we do the whole cycle again. We say, okay, I'm going to learn from what I learned earlier on. Can I learn even better? And we can see that, nope. I mean, yes, here, yes, I can learn even better, but nope, for this, I don't get a better performance. Yes, here, and yes, here. Then you ask yourself, can I learn even better? You can see, oh, not really, not this, but yes for math, yes for GPQ, no for GPQA, no for MMLU Pro, and yes for Big Bench extra hard. So you can perform the same thing for the 8B base, Octo Thinker, and you can see that, like most of the scores that did very well are usually the one at the third cycle or the second cycle or the first cycle. Yeah. So it's not guaranteed improvements for all of them. I suspect they stop at Ether 3 because Ether 4 is probably a dip. All right. Researchers, we don't really like to report negative results. All right. So my gut feel tells me Ether 4 is worse than Ether 3. That's why the results stop at Ether 3. No, if not, why wouldn't they continue this cycle all the way, right? So when you look at research papers, must look between the lines, all right? They only report to Ether 3, likely because that's the cutoff for performance after they. Because if not, as a researcher, I would say that you can continue performing this iteration again and again without loss of performance. It only goes up. Why wouldn't you report such a result in your paper, right? I suspect the reason why it stops at Ether 3 is because Ether 4 is it goes down already. All right. So this is something to take note of. If you want to use R0 to augment your data set, Number one, your model, your LM already needs to know how to answer those questions to a relatively decent way, all right? Okay, so if you already know how to answer, it can lead to much better improvements. If you don't know how to answer, it probably will lead to very minimal improvements, but there's some improvement, all right? And number two, you probably don't want to run this R0 process too many times because the performance might plateau, or in fact, it might even go down, all right? Okay, questions for this results. I think it's quite interesting to analyze these results because, you know, the procedure as described earlier is cool, but does it work? I'd say it works. It works to a decent extent, but it doesn't work forever. Okay, if there's no questions, let's move on. All right, so next, they check whether the accuracy of the pseudo label, which means the majority vote, is accurate across iterations. And guess what? Okay, it's not very surprising, but the majority vote is worse off every cycle. So what they do is basically they take the challenger at each iteration, all right, and they ask the solver at each iteration to solve it. And for the questions for iter 1, the base model can solve like 48% of the time, iter 2, 52% of the time, and iter 3, 44% of the time. So it's a hit and miss. Sometimes the second iteration, the base model can solve also. But the key thing is the solver here. You can see that the solver for iter 1, at the questions for iter 1, the solver is about 50%, about 50%, about 50%. But you can see once it reaches solver at iter 3, whoa, it can solve iter 1 really well, much better than this. And like, okay, I mean, it's not exactly consistent because solver iter 2 is downwards from iter 1. You can see that as the solver increases in iteration, it sorts of can solve the earlier problems, supposedly the easy problems. So, if you group this may be easy, medium, and hard. It's like adapting question set based on your maturity of the solver, right? And as your solver progresses, it's good to see that it can solve the easy questions much better. Same thing for the medium questions, and the hard questions, it's still solving 50% of the time, which is expected because these questions are built to be 50% solve rate for the solver. Yeah. So this is something that, I mean, it shows that the process is learning something. But what about the label accuracy for your pseudo labels? And if you look here for the pseudo label accuracy, you can see that the iteration 1, the consensus vote, very good. Iter 2 is not that good. Iter 3 is worse. So you can see that the challenges questions become more difficult because your pseudo label is getting worse off. And what you can see is that the majority vote is not enough to give the correct ground truth. Here, the ground truth, they just use the LLM as a judge. They use GPT-4o to compare the answers and see whether the answer that GPT-4o generates, is it the same as this pseudo label, right? Which actually is not a great ground truth because this can be wrong. Also, the judge can be wrong. And GPT-4o maybe is not the best benchmark for this kind of things because they don't get full scores as well. All right, so we have to treat these results with a pinch of salt because LLM as a judge is always not a very good benchmark to use. Okay, you are using two sources of errors together. It's very hard to ascertain for sure whether is it correct. Unless your judge is already like 99% accuracy or 90% accuracy, which I don't think so for GPT-4o. These benchmarks are still quite difficult, right? So maybe if they use like, I don't know, Gemini 2.5, maybe it is a bit more convincing. So I think this is something to take note of. And this is also one of the drawbacks of this method is that we rely a lot on majority vote, and the majority vote may not be correct, right? So they also did a very interesting experiment here. They basically asked, whether we can perform better with labeled data. So basically they ask the same questions to humans and then they get humans to solve it. And based on this, so there's a labeled data set of question and answers that are after the end of every iteration, you fine tune to that answer. And this is basically if you just do a supervised fine-tuning alone, you see that this is the accuracy about 49%. If you were to just do a fine-tuning alone of your base model, you get 49%. After iter 1, you take the solver and you fine-tune it. Whoa, you actually get better than the native solver just by fine-tuning with the labeled data set. Oh, you can get here as well. But you see the gap sort of closed down. It's not very consistent. Why? With extra quality labeled data, you can even perform better than R0. So let me give you my intuition why. R0 generates a synthetic data set. Question and answer. All right. The human labels is another data set. So if, let's say, we have the data set to be different, and these are likely different from R0 data set, you essentially learn from both. So if you have two high quality data sets, and over here I'm using high quality in quotation marks again because the R0 data set is not exactly high quality. There's errors, but I hope the human data set is without errors. All right. So learning from both data sets that are relatively high quality can give you better improvements than just learning from one data set alone. And here I would like to highlight something. If we use the human label data set, can you see that we achieve the R0 iter3 performance? Let me just delete this. Can you see this? We just do a supervised fine tuning. We achieve the R0 performance. What does this mean? It means high quality data set. It's better than learning from consensus. Okay, so what does this mean for our education system? If you want to let people learn on their own, you kind of still need to supervise them a bit. You kind of need to, once in a while, check in, give them the right trainings. Because otherwise you might get trends like this that, it learns and then maybe after a while it goes down. You might get trends like that. Like we don't want learning to plateau or even go down if we learn wrongly. So this is essentially the key thing for learning. You kind of need high quality data. And I can tell you this for sure. All of deep learning is about learning from data. And if you have a means to get high quality data, that's where you will shine. All right. If you have high quality data for your input pipeline, your outputs will be very nice as well. But if your input is bootstrapped from learnings of each other, you might not be able to shine that much, okay, because there will be errors. But hopefully the errors will get minimized with group learning. So two kinds of learning. R0 tells us how to do group learning. But the traditional way is if you learn from high quality data set, you might already reach the similar performance to group learning. And you learn from both is even better. But this is actually also impressive because the R0 has no labeled data set and learns as well as a human labeled data set. So what does this tell us? It tells us that actually the model can learn from its own bootstrap knowledge without human inputs for this particular problem. I think this is math, 49%. Let's see what's this benchmark. This is math. Yeah, this is for math. I mean, super GPQA, I guess the improvements will be more if you learn on the human data set. So again, they are a bit selective with their results. They probably only show those that maybe R0 can replicate human performance, maybe. Yeah. So this is something that, like, I think this is something that is interesting. And I also have a comment here. It's like, I think the gains of learning from both data set are minimal. I have a feeling that the base model already has some training on this labeled data set. If not, if you have a R0, iter3 R0, why is your gains so little from your labeled data set? Like, does it really make sense to me? I mean, it should be, I expected this line to be here. Like, why did this dip? So my gut feel tells me that some part of this labeled data set is probably the pre-training data for this LM. All right. So Pros and cons. I still think this is a good method, but it needs to be managed differently. Okay, it shouldn't be managed like how they did in the paper. Okay, let's take a look at some comparisons. So this is a curriculum learning kind of system, and we already have seen a curriculum learning thing in Voyager. In Voyager, you have a Minecraft bot, all right? And the Minecraft bot learns from the environment here, and basically the curriculum that the teacher will come up with will be based on the success and failures of the student in previous tries. So if let's say the student has not been able to craft the table, maybe we ask them to mine the woodlot first. And only after that, then we can do the crafting of table. Right, so the curriculum is adjusted based on the success and failures of your student, and it's based on the environment because the teacher and the student are in a real life environment where they need to make decisions and actions that are affected by the environment. Okay, R0's curriculum here can be very artificial, right? R0 has no need to adhere to any environment. So this is a comparison of R0, and I think R0 here is a bit more free to come up with their own curriculum compared to Voyager, but the idea is similar. Based on the student's ability to learn, we come up with something that, the student is probably able to handle. All right, so this teacher-student mechanism, I think is quite useful. All right, so we have come to the discussion session for today. So let's spend a bit more time here today. We have about 15 minutes. I do think there's some good stuff to learn from and some bad things to avoid from in this paper. So as usual, I'll be answering the questions first. Then after that, feel free to chime in if you have anything else to add. So first, R0 needs a base model to generate questions and the answers. How can we use an R0 that is not for a domain that is not in the training set of the LM? And my answer to this is you probably cannot. Okay, because you learn from a domain that you are weak at, it's like not really good. Should fine-tune the model on high quality data set first before doing R0. Okay, it's kind of like, if you don't have a ground truth, it's like, AlphaGo. Learn from human moves, then do reinforcement learning via self-play. Okay, you do that when you are not too sure about like what moves are correct. Unless you go to like AlphaZero, you can start from scratch with just a simulator. Yeah, so if you have a simulator, you have environment rewards, maybe you can learn. But in terms of these MCQ questions, if you don't have the ground truth, you see AlphaZero, when they learn from self-play, there's an objective ground truth, which is whether you win or not. In R0, there's no objective ground truth because you are basing your answers on the majority vote. And if your majority vote is already flawed to begin with, you will just learn the flawed stuff. So you can't do this with R0. You will definitely need to fine-tune your data set first. All right. So next, how can the pseudo labels be obtained if the answer is free text rather than MCQ or structured answers? So in this paper, most of them are MCQ. So if you want to have a pseudo label that is not an MCQ, you probably need to have a clustering algorithm to cluster similar response. Maybe this can be an LM. And then, you solve it as per MCQ. Like you have a pseudo label so basically your answers that are similar will share the same label. So I think this is an extra step, but it doesn't make the method any less different. You basically just need to convert your free text answers to a pseudo label. So I think that's a problem that can be mitigated and solved. Right? Next, what is missing in R0 for better solving potential? Perhaps some structure to guide answers, perhaps some high quality question answer pairs. So the second part I already answered earlier. I do think we need high quality question answer pairs. In fact, this might even beat R0 altogether if your data set is good enough. But some structure to guide answers. I would like to emphasize this point here. So rather than asking the majority vote answer, maybe you have a framework. So for example, the framework is like step one. Let me think of a framework that people normally use. I guess is analyze the question, identify variables, identify key relations needed, and then like maybe solve the question. I just came up with this framework myself. Like this is maybe for math, analyze, identify which are the things needed. Of course, different domains have a different framework. So if you guide the model with a correct chain of thought, you get better quality answers. So the question I have is that, rather than using a consensus vote, what if we do guided answer generation? And this guided process can be already pre-identified by a human to, give the right structure. I mean, you might learn this structure yourself as well as a meta learning step, but that's more complicated. Usually, I would prefer that this framework is already handcrafted to make sure that it's solvable. Like it does the answer in a good way. So if you have a structure to guide answers, maybe you can have better quality answers that could perhaps mitigate some of the downfalls of just asking the model to get the answer yourself. So I mean, the paper they also use chain of thought to get the answer, but if you have a guided chain of thought just for that domain, you might be able to solve the questions better. So maybe this could help to increase the reliability of the answers. You can also do consensus vote after this. So yeah, I think this step is still important because without a good ground truth label, you will have bootstrap errors. And this is going to be difficult if you don't have the ground truth labels to learn from. Okay, let's open for discussion. Anything you want to add for this? Are you all good? Okay. All right, let's move on then to the next slide. So the final thing is, what if there's a tie in majority vote? What if like 50% of the class says answer one, and then 50% of class says answers two? Okay, you want to try? Like, who should we prioritize? Answer one or answer two? Any good suggestions? Okay, so I went to investigate the code. In the code, basically the answer that occurs first is the selected one. So they just take they just count the answers, and answer that is first in the index of the students or of the solver will be chosen. So basically it's an algorithm thing. Yeah. So if let's say the answer one appears first, you will choose answer one. Right? Not exactly the best way to do it, but you have no choice because you have no ground truth. Right? So again, this is an issue with the method. Maybe if there's a tie in a majority vote, maybe you can send it to a superior LM to give you the answer. But if let's say you send it to the superior LM, then why not just use the superior LM or rule-based method to give the ground truth, to give the answer all the time. Right? If we ever need to do this, why not just use the superior LM, which I think might be a better approach, because learning from each other has problems. But if you can learn from either a guided version of yourself to get a better answer, or you learn from a superior LM to give you an even higher quality answer, I think that might be better. Right, the next question is an interesting one. Why do we set a 50% solve rate? Why do we want to hinge on the borderline, right? I would like to see some ablations, like maybe 70% solve rate, because this is yeah, I have, because like, maybe if you have more that can solve, the consensus answer might be more accurate. Okay, maybe 50, 60%, 70%, 90 to 100, maybe you don't learn much. But, maybe you have a 70% solve rate. You are uncertain, but not so uncertain. Rather than, is it 50%, 50% sure, 50% unsure? I think that one, you might even doubt whether you are sure or not. like maybe we are 70% sure, it's like, okay, I think maybe the majority vote is correct for this because like 70% of it is correct. But if you have a 50% solve rate, I can't really trust my majority vote that much. I think it should be a little higher. And I would like to see maybe some results if the authors want to redo the experiments. Like maybe try 70% solve rate, maybe it'll help better. Yeah. So these are just some thoughts in my head. All right. If I were to implement this mechanism, I would probably do guided chain of thought followed by the majority vote. And I'll probably set the majority vote to be higher. Right. So this is what I would have done. Because I think that like the majority vote is very important. It's your source of ground truth for this R0. And you kind of want to make sure that this ground truth is as accurate as it can be. All right. So some thoughts off my head right now. Okay, that's all for the questions. Anything else to add? You're a little quiet today. Yeah, hopefully this paper is interesting for you. All good. Okay, if not, that's all for today. So just a recap for R0. R0 is basically having a teacher and a student, a challenger and a solver. The challenger asks questions and basically tries to trick the solver to answer it correctly only 50% of the time. And then after that, the solver solves it by trying to align to the majority vote. And by keep doing this iteration of challenging and solving, we generate better and better, hopefully better and better quality synthetic data sets. And we can use that to train the LM to achieve better results. The drawbacks of this method is that it relies a lot on the majority vote, which can be wrong. And so improvements of this method might be if you have a better quality data set to use, you can use that first before you run this process. And if you could have a better way of ensuring the answer is correct, maybe through a guided chain of thought, some rule-based calculations and so on, maybe even using tools to do the question and then get the answer, that might be possible augmentations to this method that will make the majority vote more reliable. Yeah. So with that, I think this is a very interesting way to see whether LLMs can self-improve. The answer is yes, but no. You can improve, but not a lot. So we have to come up with a better way of learning rather than learning from yourself. Okay, learning from group is a great way to learn, but learning from a group that is predominantly yourself is not exactly the best way to learn. Maybe you need a more diverse set of students. Maybe you need a better way to learn from environments that already have some ground truth in it. So I do believe in a lot of learning from the group, learning in parallel. All these things are good. But I don't think this kind of method that R0 provides will lead to self-improving systems. Right? It will self-improve to a certain extent, but it will plateau off. There needs to be a lot more that needs to be done in increasing the diversity, increasing the way we view the environment and so on. So all this, I think I'll cover. I do have an idea for evolutionary algorithms, right, that are based on my readings of consciousness. And I'll probably be sharing more in the upcoming session. So I think we can do better than this. But R0 is definitely a very interesting step to self-improve. It's just that I don't think it can self-improve indefinitely. Right? Okay, with that, yep. Just ponder over that and we'll meet again next time. All right. See ya.